we've talked about the SN2, E2, SN1, E1 reactions. Um, and up to this point, for the most part, we've been starting with alkyl halides as our starting materials for those reactions. Um, we did see that we could do E1 reactions starting with an alcohol. I want to expand on that in Module 23 about some other ways we could make alcohol act as a leaving group. Okay. Um, so, first of all, let's think about why we can't just do an SN2 reaction where we replace an OH group with, say, an alkyl halide or some other nucleophile. So in this case, we might want to do an SN2 reaction where I take Br minus, which is a good nucleophile, and use it to replace an OH group. Seems plausible, but notice the problem is my leaving group in this case is OH minus, and OH minus is a strong base. Which means it is not a good leaving group. So as much as I may want to just be able to replace OH minus, I can't. So this definitely will not work. But there are ways to turn an OH group into a better leaving group. We've seen one of them already when we talked about E1, and that's we can protonate it. So if I have an alcohol and I add an acid like hydroiodic acid, HI, or hydrobromic acid, or hydrochloric acid, those are all strong acids, and those can protonate the alcohol. And we said once we protonate, that alcohol becomes a much better leaving group. All right. One thing to note, this step is definitely reversible. So that protonate, it's not going to stay in that protonated state all the time. So when we protonate, if we want to use protonation as our method of making an alcohol a better leaving group, we need to have something in the solution for it to react with right away. We can't say add H plus and then try and add another reagent. So in this case, if I add HI, okay, I do get my protonated alcohol where I do have a good leaving group now on this carbon. Note in this case, this is a primary carbon. And I ask myself, well, is there something else in the solution that can come and react with this protonated alcohol? And there is, because iodide is a good leaving group. So under these acidic conditions, iodide can come in and do an SN2 reaction, right? SN2 is the best choice here because this is a primary carbon, good sterics for SN2. So essentially, I'm protonating and then I'm doing an SN2 reaction, replacing the OH minus with I'll write this as H2O so it's more familiar. I'm replacing the OH group with an iodide group, and water is a byproduct of that reaction. Okay, so that's one possibility. What's different in this second case? Well, in this second case, first I had a primary alcohol. Now I have a tertiary alcohol. So what's different, since this is tertiary, this is sterically hindered. So no SN2. So when I protonate a tertiary alcohol, really I need to wait for my leaving group to leave so that I can have a carbocation, and now my bromide ion can act as a nucleophile and come attack the carbocation. So in this case, I'm getting the same result, but this was by an SN1 mechanism. So this was SN2 because it was primary. This one's SN1. But the bottom line is I can protonate an alcohol, make it a better leaving group, and then I can do some substitution with it. The only way this is going to work is with HBr, HI, maybe HCl, if you have that, if you want to do an SN1 reaction with Cl minus. But this isn't a reaction we use a whole lot. And the reason is, strong acids, there might be other parts of my molecule that might be sensitive to the strong acid. And so we use this pretty sparingly. The problem with acid, number one, you're dealing with very reactive reagents. The other problem, since this is often going through a carbocation, you have to worry about carbocation rearrangements. So for example, in this next case, if I start with this alcohol and I add HBr, I can protonate. Now this is also a pretty sterically hindered molecule, so I'm unlikely to do SN2 here, but what I can do is an SN1. But now I have my secondary carbocation next to a quaternary center. That can do a carbocation rearrangement, an alkyl shift. So I might have expected the product that's shown up at the top there, but that's not what's actually going to happen. What's actually going to happen is I'm going to get this other product. All right, so one issue is alcohols often encourage these carbocation rearrangements. But there are also other problems. And that comes with the fact that when you protonate an alcohol, as I said earlier, it's a reversible reaction. So yes, you do get some protonated alcohol, but it doesn't just sit in that state. So a mistake that students often make is to say, oh, I'm going to protonate my alcohol. I'm going to add H plus. And now I'm going to add, say, Cn minus and do an SN2 reaction to replace the alcohol. And that definitely won't work. Okay, I can tell you right now, this sequence definitely does not work. Why is that? Well, if you think about it, if I have a protonated alcohol, I'm going to draw it out. If I have a protonated alcohol and I react with Cn minus, well, the pKa of this protonated alcohol is about -2. So when Cn minus comes in, rather than attack the carbon, it is much more likely to just grab a proton. Leaving behind my alcohol and then HCN, the pKa of which is about 9 or 10. So this would have a K value of somewhere around 10 to the 11th, 10 to the 12th, meaning that's going to be the much more likely reaction. So you cannot protonate and then try to add some other reagent. That just will not work. So protonation, it can work in reaction mechanisms, but when we are choosing reagents to use, it's not going to be our go-to. Luckily, we've developed some reagents that are good go-tos for this. And so I'm going to just introduce you to a couple of them. So One is called thionyl chloride. That's this SOCl2 molecule. I'm not a big fan of the way it's drawn here. I would prefer to draw it this way. But you often see that sulfur drawn with a double bond, breaking the octet rule. The reason I don't like this sulfur with the double bond drawing, which I will say is the way you'll usually see it drawn, is it implies that there's a sulfur oxygen pi bond, which makes it seem like the LUMO of that molecule should be pi star SO, but there is no pi bond, so there is no pi star orbital. So in fact, the LUMO of this molecule is sigma star SCl, and that's the orbital we're actually going to attack. So when an alcohol encounters thionyl chloride, the alcohol does have a lone pair, and that sulfur is pretty electron hungry, right? And so what you have is the oxygen lone pair donating to sigma star SCl to create this intermediate down here. This reaction is usually run with pyridine, and the reason it's run with pyridine is a weakly basic non-nucleophilic solvent. So its role in this reaction is as a weak base. A lot of times we abbreviate it as just PYR with a lone pair, just to make our lives easier so we don't have to draw it out. So its role here is, now I have this strongly acidic proton. I'm going to come and remove that. And that creates this next intermediate. So the thing about this next intermediate is we now have created a very good leaving group. This here is going to be a very good leaving group. And we have also released chloride in this first step. You might note that chloride is released. Now, chloride isn't a great nucleophile, but in this case, it is going to act as a nucleophile. And the reason it's going to act as a nucleophile is because this leaving group is very good. And when I attack this leaving group, what it produces is another Cl minus, but also sulfur dioxide gas. And reactions that produce a gas, they are favorable thermodynamically often, and they're essentially irreversible, because when you produce a gas, it bubbles out of your solution and it can't come back. So this essentially drives that reaction forward. One thing to notice about this step, chloride is acting as a nucleophile, kicking off a leaving group in an SN2 way, which is why you see the stereochemistry gets inverted at that stereocenter. So when we started, the OH was wedged. Now the chlorine is dashed. So thionyl chloride is a reagent that we can use to convert an alcohol to an alkyl halide. And then that alkyl halide now has a good leaving group. Now we can add a different reagent. So if I wanted to, I could replace that chloride with any of those nucleophiles that we saw. We can use in an SN2 reaction. PBr3 does something very similar. In this case, the only difference is, instead of attacking sigma star SCl, the lone pair on oxygen is attacking sigma star PBr. And we're not producing a gas. We're not producing that SO2 gas in this case. We're using Br minus as our nuclear file in the second step. it is a better nucleophile. So we don't need as great a leaving group for this to happen. There is a byproduct here of PBr2OH. But this is another effective way to turn an alcohol into an alkyl halide. So they're useful for primary and secondary alcohols because, again, this is an SN2 step. So again, we see that there's inverted stereochemistry. So one tool to put in our toolbox to make an alcohol into a better leaving group is to use one of these two reagents. It does an SN2 reaction, gives us an alkyl halide. One more possibility is we can convert the alcohol into what we call a sulfonate ester. These sulfonates are also good leaving groups. Okay. One common one is tosylate. So we use this thing called tosyl chloride. Another one is called mesyl chloride, or MSCl, might be one you run into. Similar structure, just different R group over here on the other side of the sulfur. Again, like with thionyl chloride, what we're doing in this case is we're going to have our oxygen lone pair attack sigma star SCl. I'm just going to abbreviate this whole part of the molecule over here as R, so I don't have to draw it out. Again, this reaction is usually run in pyridine, so that the pyridine can act as a weak base and remove this very acidic proton. And that gives me this tosylate. So really that tosylate stands for, you have O and then S and then a couple of O's and then your R group. Now this is a really good leaving group because if you look at your pKa chart, you will see something like this. Listed as a strong acid. So these things, if you put an H on it, this is a strong acid, which means this group here is the conjugate base of a strong acid. Which means it's a good leaving group. Just to remind you, if you flip all the way back in the notes to where we were introducing good leaving groups, right back here, we listed these sulfonates as good leaving groups, and I said they'd come up later in module 23, so here they are. So this tosylate is an example of a good leaving group. Now, why do I need this different method of making the OH into a good leaving group? Well, the reason I like having this extra method is, notice these other two both relied on an SN2 reaction as a key step, and so they both inverted the stereochemistry. This reaction, notice there's no reaction happening at the carbon, so I retain the same stereochemistry. If the OH started wedged, the OTS will be wedged. So it gives me flexibility as a synthetic chemist to say, which of these methods do I want to use to replace my OH? I have a couple of methods that will invert the stereochemistry. I have this as a way that retains the same stereochemistry. So flexibility is good. And my note down here is, like I said, I prefer the structures that follow the octet rule. The reason being that in both cases, the LUMO of these molecules is sigma star SCl. There is no pi. There is no pi bond. So there's no pi star SO. Which I think if you draw them out with the formal charges like this, that becomes clearer. All right, so 3 different methods for making alcohol into a better leaving group. This next page is just a couple of quick activities. So what I'd like you to do is think about these, try them out, make predictions, pause the video, and then come back for, so try these next 2 pages, and then come back. All right, for this next one, I see concentrated H3PO4. This makes me think of an E1 reaction. I have 2 alcohols in this molecule. One problem with one of them is that one of them is on what we call a bridgehead carbon atom. And there's a rule that I am not even sure if I introduced back in Module 7, but because of the geometry of this molecule, a bridgehead carbon can never be flat, can never be planar. So this is never going to be able to form a double bond. So even if I add concentrated H3PO4, I'm not going to be able to remove that OH. I'm only going to be able to remove the other one. So my E1 reaction is only going to produce a double bond over here on the right, and the OH will just stick around. If you're interested in learning more about that, look up something called Brett's rule, or ask me about it. I'd be happy to talk more about it. All right, so this second one, now I have an alcohol, I'm adding SOCl2 and pyridine, so that tells me after that first step, I'm going to invert the stereochemistry. That's going to give me a chlorine group dashed into the page. So then when I do another SN2 reaction with iodide, I'm going to get iodine coming out of the page. So I'm doing SN2 followed by another SN2, which means I invert the stereochemistry twice to get back to where I started. That gives me a clue about what reagents to choose in this next case. So I want to get back to the stereochemistry I started with. So probably I'm going to want to choose one of those 2 that inverts, and then I can invert again, do the same thing. So my 2 reagents that would invert stereochemistry would be either SOCl2 and pyridine or PBr3 as my first step. That will give me something with a leaving group going into the page. And then if I use NaN3 or just N3- as my nucleophile, that will replace the leaving group and give me the stereochem I want. For this last one, I want to invert the stereochemistry just once. So this would be a case where I would use tosyl chloride. That gives me the same stereochemistry. And then when I invert, do an SN2, that will give me the opposite stereochemistry. So I want to use NaCN there, or just CN minus. All right, hopefully you did well with those examples, but let me know what questions you have. This last one was about kind of a review of a few things. Let's try it out. So first of all, TSCl and pyridine. I know that that's going to give me a tosylate with the same stereochemistry. And now I'm adding this big bulky base. Actually, I'll make a point here because I haven't really discussed it much, but this is my bulky base. This T-butanol, this is just listed as the solvent. You will see in various sources, some sources like to list the solvent every time, some sources don't. So that could be included, could be left out. But that's what it's doing there. So I'm adding a bulky base, which makes me think E2 reaction. Now I have a 6-membered ring. I have some stereochemistry going on. I'm probably going to want to draw a chair for this molecule. Not my best work. Let's try that again. Still not happy with that chair, but I'm going to let it ride. So I need to choose, maybe call this carbon 1, carbon 2. If I do this, 1, 2, I have my methyl group going up here. I have my tosylate group going down here. Now, you may remember when we talked about the E2 reaction that the hydrogen and the leaving group need to be across from each other. Notice here I have a CH3 group on carbon 1 across from the leaving group. So that means the only place I'm going to be able to go to get a hydrogen to remove that's across from the leaving group is over here on carbon 3. This hydrogen here, notice, is across from the OTS group. Because I need sigma star CO to be lined up with sigma CH, so that the electrons can go from sigma CH to sigma star CO. I would have my bulky base come and remove this hydrogen. These electrons get dumped there. The leaving group gets kicked off. So what does that give me for a product? It's going to give me a product that has a double bond between carbons 2 and 3. Oops. Between carbons 2 and 3, and still has the methyl group on carbon 1. So that's a little review of E2 and dealing with stereochemistry. Often when we're doing eliminations on 6-membered rings, we want to think about these chair structures. All right, and that is all of Module 23. Let me know what questions you have.